Did you know aluminum cans have a plastic liner on the inside? Not gonna lie, I'm curious to see what that looks like. Let's go. We're gonna start by making a sodium hydroxide bath. We're gonna scuff up the outside of the can with a little sandpaper and then immerse it in the sodium hydroxide bath. The reaction is between sodium hydroxide and aluminum, which liberates hydrogen gas, the bubbles you see here. It just fell over. Something happened. What? This experiment was totally worth it. Share it with someone who needs a little science in their life.
Don't be suspicious.
So this just happened. I got my favorite bottle of purple drink, but something seems off about it.
Don't be suspicious. Don't be suspicious. Don't be suspicious.
Maybe it's the beaker? Okay then. Hey, good news. It's experiment time. Today we're going to heat some sulfur and see what happens when we rapidly cool it. We use a powder funnel to transfer the sulfur into a big test tube. Then we're going to use this old crusty meeker burner to melt the sulfur and see what happens. Now that it's nice and molten, we're going to quench it quickly in a water bath. It's very stretchy. I got a special guest with me today. I'm trying a new experiment, never done it before, and I'm doing it with one of my colleagues, Adrian Dingle, who's right there in the backdrop. We're reacting aluminum, which is in a powder form, with some iodine, which is in this brown glass container. We're gonna grind up the iodine into fine, fine powder. About 2.3 grams of aluminum powder, and there's about 6 grams of iodine here. Now we're gonna mix it up. Pour it into an evaporating dish. Make a little crater for some water. All that's left is to add some water to initiate the reaction. That's pretty cool. Not too bad. We'll try it again. Let's give it a try. All right, so you can see that it's hot enough to catalyze the oxidation of the acetone that I put in the beaker. And now I'm just going to submerge it. And yes, acetone is flammable. Now you know. I'm going to show you something, and then I want you to try and explain what's going on here. So we have some steel wool in an evaporating dish on a digital balance, and we're going to light it on fire with a 9-volt battery. Watch the mass. So why did the mass go up? Tell me in the comments. Today I want to show you how I make dry ice. I start with a tank of compressed carbon dioxide gas. It's connected to a little contraption that allows rapid expansion of the compressed gas. Let me show you what it looks like assembled. It's basically a box that gas can come out of at a particular rate. Now all that's left to do is open the valve. Let's see what happens. Okay, now it should be filled with dry ice. Let's take a look. And here's the finished product. Dry ice ready for some 2-to-1 ratio by volume with oxygen in the can. So this is the aftermath. I tried to play around with this little bulb of super hot molten iron and kind of had a little eruption. So hot. I can barely put my hand close to it because it's radiating so much energy at this point. There's actually a little bit of glass encasing the iron because it melted a bit of the sand. That's why I had to use the sand in this demonstration. Sand bath prevents it from melting through the bottom of my fume hood. I'll post a follow-up video where I show you what it looks like after we let this cool down, because it actually makes a little glass egg. It looks like a little dragon egg. You can crack it open and see the iron inside. It's pretty cool. So what can you do with rust and aluminum? Actually something pretty fantastic. Check it out. The specific flavor of rust we're going to be using is iron 3 oxide. And the aluminum we're using is aluminum that's been ground into a fine powder. We're going to pour it into a flower pot. Final step is to add glycerin, close the hood, stand back, and watch. That is a pool of molten iron with a little bit of glass around it. Thermoplastics. They shrink when you cook them. We're going to start with a plastic water bottle and add a catalyst. Next, a liquid that generates a lot of heat when it comes in contact with the catalyst. Okay, so my first attempt did not shrink very much, and I made a huge mess. I'm going to post another video of this where it actually works, but let's pour some more in just to see what happens. Maybe we need a more direct source of heat. Not every demo is a success. I want to talk to you about something that's really important right now. This stuff and why you should be using it. First, a little context. You've probably heard about the coronavirus a lot lately. This is my attempt at drawing an example of the coronavirus. Notice that the outside of the virus is labeled lipid bilayer. That's going to be important in just a minute. The other big component are the guts of the virus. The RNA guts. That's what makes you sick. Soaps can break down this lipid bilayer. They can basically cause the virus to rupture. And they do that by breaking apart these intermolecular attractions that hold the outside envelope of the virus together. This works because soaps have reasonably strong attractive forces that can form between the lipid bilayer and the soap molecule. If I had to model it, I'd kind of do it like this. This is the virus. Wash your hands, stay safe. Everyone always wants to know how it ends. This video's got some spoilers. This thermite reaction between iron 3 oxide and aluminum makes some aluminum oxide and some iron. I'm sure you remember, if you've seen the videos over the weekend, that the iron is actually molten. So the question becomes, what does it look like after it's cooled down? Let's take a look. So my chunk of iron is actually missing. I can make more. Now we just let it cool. So now it's definitely cool enough to handle. It's got a pretty strong neodymium magnet, which iron should be attracted to. I've got a pretty cheap ping pong ball, this one, and I melted a little tiny hole in it. Can you see it? Can you see it? Can you see it? Let's see what happens when we put it in liquid nitrogen, take it out, and let it sit on the tabletop. There's our liquid nitrogen. In you go. I want to fully submerge it. Using a pair of tongs to hold it at the bottom so that it gets filled with liquid nitrogen on the inside. I think it's full, so let's take it out. That is not very pretty, but that's hot water. And here we go. Whoa! That was worth repeating. So what do you do when somebody accidentally leaves a bottle of potassium permanganate and a bottle of glycerin in your lab? You put them together. Those eyes. A little bit of permanganate. And let's grind it up. Now we're just going to pour a little glycerin in, see what happens. That gives me an idea. Let's use that reaction to set off another reaction. That's the next one. In a lot of the videos that I post, you see me use a magnetic stirring bar. I want to show you how we actually get the magnetic stirring bar out after a demo's over. You use a retriever, of course. Just like that. Sometimes a reaction is hiding in plain sight. Take, for example, the neutralization reaction between sodium hydroxide and hydrochloric acid. We can also use heat signatures to let us know that something's changing. In this case, the reaction's exothermic. So I'm going to show you what it looks like through the lens of a FLIR thermal camera. The camera I'll be using, it attaches to the bottom of my iPhone, and it shows you heat signatures by interpreting infrared radiation that's emitted by matter. And now the hydrochloric acid. Let's light something on fire. The gas will come out of here. Let's make some bubbles. It's a little messy. A little less soapy water.